All right. So today, welcome to episode 2. I have not. I haven't not given this lecture as such before, because the last time I taught this class, it was just a bunch of me scribbling. So hopefully this will be a lot better. The two instructors who taught this class prior to me teaching it, or in between, did a really nice job of pulling together my scribbles into an actual slideshow. So hopefully that this will be more efficient and more understanding. As I mentioned last week, the first 4-ish weeks of this is me talking about sort of general civil engineering skills with sort of the technical stuff ratcheted down, so that you can basically do your project. So this is the beginning of that. Any questions on the project? Has anyone read it yet? A little bit? Okay. While we're still early in the semester and you don't have a ton of homework, I would suggest trying to read through that, and it will make more sense as after today. So, okay, some of this stuff some of you will already know. It'll be review, but it'll be pretty quick and efficient, hopefully. So, all right. So, topography or topo maps. I'm guessing that most, if not all of you, have had some experience with topography and topo maps. This is actually way more common than it was when I was your age, because of all the Google Maps and things. How many people have ever turned on the topo version of Google Maps? Okay, that's most of you. That's good, right? So there's like a regular street version, there's a satellite version, and then there's a topo version, which will show you all of this, which is really cool. It used to be that you had to like get out actual maps, but nowadays, and I did post this slideshow in case you're wondering. Nowadays you can zoom in and Google will automatically adjust the topo lines, which is really cool. So so here is a pretty cool shot of flat top if you've never seen the actual topo lines, but are familiar with the topography. Topography, of course, just means, I guess I don't have a good definition of topography on here, but topography is the 2D expression of the 3D land surface, right? And the easiest way to express that, there are actually multiple ways to express that, but the easiest way is by these what we call constant elevation lines, right? And so each one of those little brown lines that you see on the map represents, if you were to walk along that line, you would stay at the same elevation, right? And so that is why flat top has a big ring around it, right? Because it's flat, and so there's no peak, right? So if you stare at topo lines long enough, you can actually see the contours, right? It's kind of like viewing the matrix, right? How many people have never seen the matrix? Okay. If you're going to be an engineering student, you need to watch the matrix, right? Because there's going to be a bunch of references. I reference it in my structural analysis class. And then a pointier mountain are like these guys, right? Now, it turns out that you can't tell the difference between a mountain and a valley without reading those numbers, right? Because if this line was lower, see that, right? But if this line was lower than this line, then that would be a hole, not a mountain, right? And so you have to actually read the numbers to know. Some other rules about contour lines. They cannot stop and they cannot cross, right? If you think about that, what would that mean? 2 lines crossing, right? That would mean like there is one version of land that's at a different elevation than this another piece of land at the same spot, right? So you could actually have that. That's called a bridge or a tunnel, right? But we don't have that on maps. Same thing with a line stopping, right? If you have a wall, so if you have, if I were to look at a wall from the side, and there's land down here and land up here, we call that a retaining wall. And the way that looks in a topo map is, if this is your wall, the contours will kind of come along and then hit the wall and basically run along the surface of the wall and come out the other side. And then, maybe you have another one and it comes in and runs along the surface, and another one and it comes in and runs along the surface, right? So they're not stopping. They look like they're stopping because it's a vertical plane, but they're basically just all stacked along the wall, which leads me to the third point here, which is the spacing indicates the steepness, right? So the farther apart the lines are, the flatter your slope is, the closer together they are, the steeper your slope is, which is one of the reasons why if you look at topo maps a lot, especially mountains, like if you're hiking, you can kind of start to see the topography, right? Because you can kind of see that this area here, like they kind of get close together, it starts to almost turn into shading, and so that indicates a really steep area. And these areas with the big white is sort of a flat area, right? So and then typically we have, as in this map, you'll see that the major spacings are darker, right? So in this map, you see that it's hard to read because it's a little fuzzy, but it looks like each one is at 400 feet. And then the minor spacings probably are at 100 feet. Oh, actually, so this happens a lot, actually. Not so much in civil engineering versions of this, but in hiking map versions of this. So there's 5 contours in between 1, 2, 3, 4, 5. 5 contours in between 2,000 and 2,400, which means it's not 100-foot increments, right? That'd be 100, 200, 300, 400, 500. And so they're actually in like 80-foot increments. And this happens all the time. You end up with these random, just because they're always doing like 5 in between whatever the major increments are. So you have to be a little careful about that. So, okay, so that's the basics of a topo map. The other thing that I like to show, or I will attempt to show, that's maybe at my own peril. So here is a 3-dimensional version of an older version of your the piece of land that your project will be in. It's a little bit changed because the river over here, or the stream is basically going along the left-hand side and not connecting to the river. This is, like I said, this is an older version. And so if I were to create if I wanted a contour map, one of the things that I could do is cut it, if I can, something like that. And if I split it along that plane that I just created, and then hide one of them, two of them, right? So now I'll turn off the yellow, right? So I cut it at a particular elevation, and I ended up with basically this line and this line, right? So that's, if I were to cut it at a different elevation, then I would end up with different lines, right? So you're basically just slicing your surface or your volume in horizontal planes. That wasn't the best line, but it's okay. So the other thing, or one of the things that you can do, or one of the things that we do, so this is modern civil engineering practice, is basically to do things in 3 dimensions. So you will build surfaces. Some of you maybe already have seen this in 3-dimensional models, kind of like this one, although this is the different software. But old practice is to do things in 2 dimensions, right? Because everything had to be laid out on paper. And And the cool and the 3D version of this is really cool, right? Because you end up they go out and they survey, you know, which you've seen in your surveying class, right? They go out and they survey, they create the surface as a bunch of triangles, they in 3D and points in 3-dimensional space, and then when you go to tell you design in 3 dimensions using different CAD softwares like Civil 3D. Really? I don't know what just happened. It's coming back. Maybe. Oh, that was weird. Okay. Share my screen again. Yes. Um, you you design in 3 dimensions, you export things into 3 dimensions, and they actually have like GPS on the bulldozers, right? So if the bulldozers are like, trying to cut the land, they've got like these little things that stick up on either side of the blade that are GPS sensors, and the bulldozer driver can actually see if he's doing it right. So everything's in 3-dimensional and digital, right? So no longer do we actually do things by paper. I don't know what's going on with this, but it's the first. Um, so but it used to be, and if you're doing an early sketch version, one of the ways that you can get a sense of the land is to cut a section through the land, right? And so this is an example of what that would look like. And so here, the heavy line is the section, the heavy black horizontal line is the section that I'm cutting. And what you'll see here is that I've drawn a red line at each location where the heavy black line intersects with a contour, right? And then down here, you can see that I drew a little grid. I've got 60 feet, 100 feet, 140 feet. I go up here, and the easiest place to start is actually at the top, right? And so I start at 180, and I say, okay, my red line hits there and there. I can tell, well, I can't tell actually, but I know that this is like 190, and this is 200. And so therefore this point right here is somewhere between 180 and 190, right? So I stick a point there, and then I can just draw straight lines basically in between, and I just keep going with that, right? Here's 170, here's 160, and I just draw straight lines, and then I have an image or a section cut of, and my pen's gonna die, a section cut through the land of what that would look like, right? So that would be the same. Basically, I'm doing a hand version of, if I were to split this, so I wonder if my computer can't handle this. This might be a problem. It's a fairly new computer. It's trying to like run Fusion, run Zoom, run PowerPoint, not PowerPoint, PDF. All right, it's not going to allow me to do that. So this is Fusion, which is AutoCAD's version of SolidWorks. It's a pretty resource intensive program, so that might be what's killing me here. It's that if it recovers, then I will cut a section. But hopefully you get the idea, right? Is that so we call that a section cut. It's actually fairly rare to just randomly cut a section through the ground. Much more common is something that we call a profile. And so, and then here's another version. I actually forgot to do this, but this is an activity that you could do on your own, right? And it's basically the same as before. Right, you draw vertical lines at each contour, and you're going to end up with a cut through there. That's, well, I won't spoil it. Right? Hopefully you can kind of see what that's going to look like. All right, so the second part of this, once you have an idea of the land, right? The second part of this is, okay, I want to put a road in. How do I define my road, right? If you're a civil engineer and you're working on pen and paper, and again, in full-blown design mode, we do this in three-dimensional digital models, but people still do this by hand. Typically, it's in what we call the schematic design phase. So the schematic design phase is generally less than what we call 10% design. So it's sort of an early, throw a dart at the wall, try to get an idea of what we're talking about design. A lot of times people still do it with pen and paper. I know as a structural engineer, I still do it as I did it as with pen and paper, except it's of a building, right? And so I would sketch out what the structure would look like pen and paper because it takes way less time than doing something full-blown digital. So, so how do we define the geometry of a road? So first of all, first point there is we define it using the center line, right? So everything is the center line. So we don't really talk about, the only time we talk about the edges of the road is basically in relation to the center line, right? So the edge is, parallel to and 15 feet away from the center line, that kind of thing. And then secondly, we define that geometry using geometry, right? So we don't just sort of draw squiggly lines on the paper. We actually will use numbers to define the road. So for example, here you'll notice that there is a radius of this curve, right? And then here's a radius. And then from this little circle, which is impossible to probably see, to this circle, it's a straight line. And sometimes it used to be actually, I remember back in my day, that sometimes they would actually give a compass bearing of that straight line, right? So it would say, what that is about, let's call it 102 degrees, right? So it's not how you would write it, but I can't remember how they would write it. But you could, back in a long time ago, that's actually how they would lay out the road, right? They would take a compass and they would like shoot a straight line at that compass bearing. With GPS, we don't do that anymore. But that's how you define the road, right? Straight lines and curves. And of course, whenever a straight line hits a curve, they have to be tangent, right? You can't have a kink in your road. Drivers don't like that, right? People are bad at driving kinks. So you always want it to be nice and smooth. And then the way that we define where stuff is located is these numbers on here, which we call stationing, right? And so you'll notice that I have these little tick marks in the center line, and each tick mark is aligned with a number. And so this is in our case, we do it in 100-foot increments, right? So this is a 200, 400, 600. And the plus is always, this is sort of a drawing standard. The plus is always located at the tick mark, right? So you always know where that lies. And then from there, you can define everything else, right? For example, the transition point here between the curve and the straight line occurs at some number, which I haven't defined, but it's probably like 352, right? So you would say something like, at station 352, transition between curve and straight line, right? So that's how we define everything, is by that stationing. And you can see that this defined road is about 2,200. I haven't actually labeled this bottom one, but there's a tick mark right at that tunnel. And so it's about 2,200 feet of road, right? Okay. Obviously, in other countries, they do it in meters, right? And that works out nicely because it's in kilometers at some point, and we have to deal with feet and miles. Here we are. So that's how we define a road in the plan dimension, right? You think is it going to recover? Maybe, maybe not. No, it's not looking good. All right, let's shut that down. Maybe that will help. So the next thing is basically the combination of a section cut and a roadway alignment. And so we call this a profile, right? So the profile, and I had this, if I could use Fusion, you could see, basically it is if I were to cut this surface or this volume, if you will, and along this magenta line and basically take away all this so that all you can see is the cut along this line, and then you stretch it out or straighten it out, right? Because it's going to be a curved surface, vertical surface cutting along that. And then if you straighten it out, and so you can put it on a flat piece of paper, it's going to look basically like this, right? And you can see that I still have my stationing down here, right, between 0 and 2200. And you can see like there's the top of the hill here is at about 700. The stream here is about 250. The river is at about 1200. And so if we look at that, you see the same thing, right? Top of the hill is at about 700. Stream is down here at about 250. River's down here at about 1200. And so that's what I'm doing is I've already defined. So you can't cut a profile obviously until you've defined your horizontal, right, in your stuff in plan. So then once you cut your profile, then you do a similar thing to what I did here, except it's harder because now you're talking about, basically coming up with the intersections of the contour lines and the stationing, right? So you have to kind of measure along the contour or measure along the stationing and figure out where your contour lines are hitting, and then you can construct your profile. And again, you can do this by hand, right? It's not that hard. You can print. We used to do it by printing things out on big pieces of paper and then just at scale, and then just measuring, drawing a line and then just measuring the distance between the contour lines. One thing to notice here is that it is exaggerated 2 to 1, meaning, for every foot length, right? This is 100 feet. And so these are 20-foot increments, but they're actually 40 feet apart if you were to actually scale it, right? And in this case, in this particular piece of land, that's not super necessary because it's super mountainy, but in other places, it's you wouldn't be able to see the curves if you don't exaggerate it vertically, right? Because everything's so flat. I always joke that we go back to this. What does the contour map of Florida look like? Huh? What's up? It's well, it's a white sheet of paper, right? Florida. If you've ever, how many people been to Florida? Well, that's a lot, actually. It's the flattest state in the world. It's the most ridiculous thing ever. Like it's so stupid. Everywhere you go is just flat. I lived in the Florida Keys for a summer, which is even flatter than the rest of Florida. It's just ridiculous. Like 2 foot, basically if you look at a contour map of Florida, the contours are in like 1 foot increments because it's so flat that that's the only way you can see anything, right? If you looked at a contour map of Alaska at 1 foot increments, it'd just be black, right? So anyway, it will be underwater in about 50 years, so that's fine. Especially the Keys. Okay, so stations. So oftentimes the profile is used to show both existing and proposed ground, right? So in this case, I've shown you the existing, but what we're trying to talk about here is a proposed road, right? And it turns out that if you were to make a proposed road here, it would probably want to look something like this. Why can't you just go up and over the hill? Well, that would be too steep to drive, right? And so like, for example, in your project, you're limited to a 6% grade. 6%, what does 6% means? That means 6 feet per vertical per 100-foot horizontal, right? And so you could draw that on here by just, scaling up 6, which would be about that, and then going 100, which I actually hit it pretty close, right? Something like that. So you can kind of figure out how steep you can drive, and then you go, well, I know that I'm starting at a tunnel that's over here that's at 170, I think, And over here, I can't remember, I think it was also 170 maybe. It's listed on here. Oh, this one's 160. So, oh, I hit that. That's actually, it's right there. Something like this. I don't know. Right. And so you've got limits to how steep you can go. And so you have to cut through the land or fill in the land to get within those limits. Right. We also have something called vertical curves. We're not going to talk about that too much in this class, but the reality, but what that means is that, if you have a straight line that's like this, and you have a straight line that's like that, right? So this is your car, right? All cars look like this, right? Driving up the hill, right? And so you don't come to a point, right? Same thing as the horizontal version, right? You'd like go over, and so we do things like vertical curves that look like that. That gets more into traffic engineering, which will be in your senior year. So we're not going to get too excited about vertical curves. But if you think about vertical curves, it's kind of neat because you actually want your vertical curves to be kind of big, because it actually has to do with the sight distance that you can see over the hill, which is kind of neat. I never really thought about that until, and your headlights too, actually. So, but vertical curves do exist, and just so you know. Okay, hit everything on here. I think so. And obviously this is a bridge, right? And so this is going to be part of defining your bridge, right? Can I build a giant abutment right here and right here and fill all this in so that my bridge is only this long? Yes, right? But there are implications to building super tall abutments and filling them with soil, right? Or is it cheaper and better to build a little abutment back here, only fill a little bit with soil, and then have a super long bridge, right? So those are decisions that we make all the time. And if we back up to this, those decisions, the horizontal road alignment that you choose is going to be affected by all of that stuff, right? And so we'll get into that a little bit more. So, all right, the third piece of this puzzle is called sections, right? A roadway section. And so this is, of course, hopefully you can tell that you are looking at a cross section of the road as if you're standing looking down the road and someone were to just cut through the land. It would look like that. So if you were a vehicle, I always try to look like this. So you're driving, it's not a very good one, but you're driving a Hummer. It's coming straight at you. Right. So here's the center line. It's not tall enough. It's be taller. So the center line of the road, everything is based off center line, right? When we talked about it in the plan view, right? We call this plan view, bird's eye view. We defined the center line, and so now we're going to define the cross slopes, right? So this 2% is the crown or the cross slope of your road. Why do we have cross slope? Drainage, right? There's actually two reasons. If you crown it, it's for drainage. If you have it all going one way, it's for super elevation for your curve, right? So it's like a racetrack. But mostly we don't do that, right? We do that on fast roads, but not so much on slow roads. Typically we care about drainage. It also is defining here what your road's going to be made of, right? So this is an actual cross section that I stole from the Kincaid plans. So they redid the road to Kincaid in 2007, maybe something in that neighborhood. I didn't live here before that, but I kind of wish I had some pictures of like what that road looked like before, because it looked really sketchy. And so you'll see here that they put in 24 inches of type 2 classified fill, right? So there's all this stuff which you'll learn much later about the different types of gravel and fill and backfill, right? It has to do with the amount of coarse material, fine material, chemically inert material, all that stuff. You don't want any organics or peat in there, that kind of thing. So you got 24 inches of type 2 fill. Then you've got 18 inches of type 2A fill. And then you've got 2 inches of leveling course, which is a pavement, and then 2 inches of, I don't actually know what AC pavement stands for. So there's 4 inches of pavement, right? And so that's telling the contractor, first of all, what to bid on, right? And then second of all, how to build it. And so this is, and then down below here, it says stations 2600 to 3250 and 70 to 7885, right? So, this is again, not from my example, this is from Kincaid, but, basically you're saying, from something like here to here, it's going to look like that cross section. And then, maybe from here to here, it's going to be a different cross section. And this is how you would define the different widths of your road as well, right? Because you'll see here, this is defining a 12-foot lanes, 4-foot shoulders, and then 3-foot sort of gravel side thing before the ditch. And so like if the ditch goes away, then you need to define a new cross section. If you add a new lane, you need to define a new cross section, right? So that's kind of how it's done. And it used to be, and I don't know if they do this anymore. Actually, I think they do, although I don't know if anyone looks at them. This is the design plans. They would sort of do it like this and sort of show you, okay, this is the cross section. It goes from here to here. But then at some point, between the advent of hand drawings and 3D modeling, sort of in that 30 years in between those, because hand drawings is all just this, right? And then the contractors would be smart and they would know how to translate that into real ground. But then somewhere when CAD was a thing, but 3D modeling wasn't, they would actually print out every single cross section of a road, right? So 100, 200, 300, 400. It would be like 25 pages with 5 cross sections per road per page at 24 by 36 printout, and you just have pages and pages of road cross sections, right? I think they still do that, although I don't think they actually print them. They probably just make digital copies and stuff. So I've seen the version for Habit when they did a Habit, so I think they still do it. But like I said, I'm assuming the contractor doesn't really use it per se. But that's what a cross section is, and so. Let's see if I missed anything. So there's a note here about existing ground. So in here, you can kind of see this dashed line. This is the existing ground. And of course, your proposed ground, which is this ditch, has to meet up somewhere at the edge of your cross section with your existing ground, and that will define basically how wide your project is, right? And you'll notice here that it's, there's a 2-foot definition that you have to clear and grub past where this is going to hit, right? So sometimes they don't show existing ground because you're going you're talking about a cross section that covers hundreds of feet, and so the existing ground might be too complicated. All right, here's another section. This is from my example problem. And so here is station 7. So if we go back here and look at where station 700 occurs, that's right here, right? And so if I were to stand looking up station, right? So I'm going to stand here and I'm going to look to the right. Then my ground is sort of falling off to the right, right? So a few feet away from the road is my 200, and then that's probably hundreds of feet from the road is 180. And then if I go and look at my profile, if I cut a section here, I notice that my proposed road is way down here at about whatever that is, 170, 165, but my existing ground is way up here over 200. And so the only way to make that work is to cut all that land out, right? And so that's going to look like this, right? And so there's my existing ground. It's kind of falling off to the right, but I have to come through here with an excavator. First of all, I have to define this slope, right, which is typically 2 to 1. Why not steeper than 2 to 1? Why don't I do a slope like this? It'd be way less work.
for safety, dirt collapses it.
Yeah, we don't want to kill anyone, right? Dirt collapses, especially with earthquakes, right? Um, yeah, we drainage. There's lots of reasons, but the big reason is because we don't want it to fall into the road, right? So typically it's 2 to 1. Sometimes it's 1.5 to 1, but then you have to like use something that's sort of gravelly, and has some good soil characteristics. And so typically it's 2 to 1. And so with a 2 to 1 slope, if we have to go from, let's say this is 150 up to 200, so I'm cutting down 50 feet. That's a massive road cut, which means that I have to go 100 feet, right? And then I have about a 30-foot road, so that means I have a 230-foot road cut, right? Which is huge. You'll also notice that I have a little drainage ditch in here, right? Because if you don't have a drainage ditch and you have this giant slope, then all the rain's going right out onto your road, right? So that's no good. You also need somewhere to put your snow. One option to reduce that, let's say somebody had a house here, right? One thing you could do is build a retaining wall, right? So a retaining wall typically would look like this. Sits underground. Kind of looks like that, right? And so now you've got regular undisturbed soil back here, and then you basically have this vertical wall alongside your road, right? What's kind of amusing about this is that we do this all the time because the way our country is set up is that this person was here first. You can't take their, you can take their land, right? But if you're going to have to take their house or their structure, then a lot of times you can't do that, right? And so you have to do some engineered version where you do a retaining wall or some other solution. You can buy their house, but that gets sticky, right? And so what's funny about this is that a lot of times it turns out that sometimes it would actually be cheaper to buy their house and demo it in the long run than to build this massive retaining wall, right? But we don't like to do that, take people's houses. So there's a great version of this at the intersection of Tudor and Lake Otis, right? There's a huge retaining wall on the southwest corner, which is protecting St. Mary's Church, which is behind it. And before they widened that intersection, that retaining wall was much smaller. And they did take a bunch of St. Mary's land, but they made the wall really, really big and really, really expensive in order to preserve parts of the church behind it. So, okay, so this is a big, what we call a cut. We also have, another version of this, which is, I don't think I have an example of, which would be a fill, right? So if the land were down here and you have to put your road, but you need your road to be up here, then you would just fill in, put your 2 to 1 like this, 2 to 1, and then you're filling land in there, right? Okay, so here's a couple more examples. This is the Kincaid job. You'll notice that it gets really messy really quick, especially if you don't have any colors. But here's kind of an example of what it looks like. So you'll notice that they began the project at station 2600, right? So the stationing doesn't have to start at the beginning of the project. In this case, it probably started at some defined point, whether it be, I think it was actually like at the chalet or somewhere. And so that's where they started the project, and you can see this dark line is defining the pavement, the new pavement, right? And then you can see kind of all the stuff that the survey picked up, the trees and the brush, and there's some contour lines in here, and then there's a gas line or something in there, and a tunnel. And so this is kind of they get really busy, right? So lots of stuff in these types of plans. Here, you'll notice that there's a radius. It's not actually defined on here because probably what you have is somewhere else. Because this is such a long, busy job, there's probably a chart somewhere, right? And it'll say like station whatever, and then radius of curve, and then maybe other information like width of road. And it's got like, you know, hundreds of points, right? So it's, instead of mucking up the plan, then you just do it that way. So, okay, so how do we know how tight of a radius that we can go? Well, this is basically based on the speed limit, right? If I assume most of you have done a fair amount of driving, right? And you know that you can't take a really tight turn at, you know, 80 miles an hour, right? And so it turns out that there's this nifty equation right here, u squared over 15 times the quantity E plus F sub S. U is your speed in miles per hour. E is your super elevation, right? So again, if you're building a NASCAR racetrack, right, and you want your cars to kind of go up on the side like that so that they can take a tighter current turn, then you can super elevate your roadway. Like I said, for slower roads, we don't generally do that. But, and I thought I gave some guidance on that. I'll have to find that and add that. But typically, you know, 2% is kind of the most that you would ever super elevate a road, a regular road. Highway is a little bit different, but regular roads. And really, a lot of times it's 0. And then there's this F sub S, which you can get out of this table, which is the coefficient of side friction, right? The idea here being that as you go faster, the coefficient between your tires and the pavement reduces. And so you can kind of see the number goes at slow speeds from around 0.17 to fast speeds around 0.12, which is kind of interesting because it means that you have 2 variables in here that are based on speed, and you could probably make one a function of the other, but traffic people like charts for some reason. I don't see why you couldn't make this just math, but for some reason it's always a chart. Yeah.
Do you add to the speed limit to count for people's speeding? Like, do you add?
No.
No.
Well, you can.
Yeah.
Yeah, you can. So sometimes, I haven't designed any roads in Alaska, but I know in Massachusetts, they would do things like, you know, the design speed. There would be a design speed and a posted speed,
Yeah.
and those would be different, right? So you might be like, the design speed 75, posted speed is 65, or the design speed is 50, and the posted speed is 45, right? But sometimes you don't do that because, and you do things called, there's things called traffic calming measures, right? Where you like, you know, like at Kincaid, they have the speed limit signs that flash at you if you go too fast, right? So they try really hard because the road is not designed for, so good question. So in this case, this example, I'm not going to go through this whole example, but oh, I thought I had it. Oh, I thought I had a, so this example is, this is kind of a fun little like math problem where the radius that it have is restricting the posted speed limit to 63% of the rest of the road. And so how do you, you know, what would you have to modify the curve to be in order to get to the full speed limit? So you have to kind of go through that equation twice, because you, or not twice, but you have to figure out the design speed. Or yeah, no, twice, because you have to figure out the current speed, multiply that by, or divide that by 63%, and then go back through it again to figure out the correct radius. Essentially, right, if you have a tight curve, and you see this all the time in highway jobs, if you want to make the road faster, then, you know, you need to make the curve have a bigger radius, right? So it'll look like that, right? And you see this all the time where they're you know, cutting out a hill or removing a house or doing something to basically make the curve, you know, less aggressive or less curvy, if you will. All right, so I thought I had in here an example problem where I actually showed me using this equation. So I'll add that in. It's pretty straightforward, right? This is just basic algebra. So, all right, and then here's a quick view of the Kincaid job of what the profile looked like. It's not that exciting. it is kind of interesting in this particular job. You don't see this all the time, but in this particular job, they actually showed the existing ground at both edges of the road. So that's why there's 3 different dashed lines, right? So they're basically showing it along the existing ground along the center line, the existing ground, I guess, over here, and then over here, right? And so that's why you have these sort of 3 different lines. You'll also notice that you can see the tunnel, which looks like that, right? And again, it's vertically exaggerated so that it doesn't look silly, right? If you don't vertically exaggerate things, a lot of times everything's just flat and you can't see any differences. So you vertically exaggerate it, the circular tunnel turns into a big oval, that kind of thing. Okay, and then the last thing about this is, or one of the last things about this is the costs related to what I was talking about, which is the cutting and the filling. So this is a screenshot I took of me cutting, which I could do, but apparently my computer can't handle it. Cutting a cross section of road through that surface, right? And so, and the way that, in this case, the way that I did that is I just sort of defined that cross section that looks like this. Right? I took the cross section that looked like that, and then I just cut through the surface or the volume using the curved profile. Now, what I couldn't do, because that software won't allow me to do that, is I couldn't follow the vertical profile, which is this guy, right? So basically, I just cut that cross section flat because that's all I could do. But Civil 3D, you can do that. You can create a section, you can run it along the horizontal path in both the horizontal and vertical directions, and so it will cut through the land basically as you would do in real life. But the result of that is that you end up with being able to calculate basically this area of ground that, basically the volume that you have to cut, right? Now, if you think about this, if you're sort of able to visualize this, which is kind of hard when you're new to it, but if you're able to visualize this, you can tell that the actual volume that I'm going to cut there, that is a complicated calculation, right? I've got slopes going in all 3 directions. I've got a surface topography. I've got a profile that's changing. And so the software can do it, right? That's if you define this all in Civil 3D and you create your volumes and you create your cross sections and your profiles and your plan, and then you cut and you define both the cut and the fill, then the software, it's all digital, it's all in there, and it can just do that math for you. In this class, you are not expected to have that skill set. And so much more, and like I said, that's something that's expensive, right? It takes engineers months, to do all of that digitalization and have all those skills in Civil 3D. And, the civil engineer, PE above the EIT who's doing all that has to have this, has to decide where the road's going to go and all this stuff. And so the schematic version or the early version of this is to just do it by hand. And so the idea there is to kind of basically estimate, and I'm going to run over into next week, which is fine, which is what I figured would happen. But if we take a look at our profile, we can see, well, we're going to be cutting through here, right? And so if I look at that, I could probably guesstimate and say, well, that's probably about like that, right? If I wanted that to be a square, it's probably, that-ish, right? If I were to sort of, guess that the volume or the area of this sort of curved shape into a square, it would probably be something like that, maybe a little bit more. Right? And so now I know that that goes from like 450 to 950, right? So I've got 500 feet of that. And what does that cross section look like? Well, it looks like this, right? And so I can come up with, this is a relatively simple geometry, right? It's a trapezoid. I could probably flatten the bottom here and flatten the top, and I could calculate the area of that trapezoid. And then I can multiply the area of that trapezoid times 500, and I have my area in cubic feet, right? And then I can say, okay, well, that's my cut. Here's some fill. Over here is probably some more cut, right? It's actually should be a little lower than that. And so I'm going to have some more cut over here. And so I can kind of, again, I can do a similar thing over here. I can probably come up with some sort of square volume or square cross section that looks like that and kind of guesstimate, right? So that's the idea, is to just sort of come up with something that's close-ish, right? And so I did a couple of examples of that. If I can get there. These are I just pulled out some of the important numbers that have to do with your project. All right, so like I said, this is going to run over next time, but I'll give you the short version. Basically, I did two different designs. The first one looks like this. It has a 45-mile-an-hour speed limit, or design speed, I guess is a better way to say. And I did the math on that, and I ended up with an 833-foot curve, right? And so I put that curve in here, and then there's a straight part, and then there's an even bigger curve over here to make that work. My profile ends up looking like this. Here's one cross section. The area of this, as I described, is 6,030 square feet. And then that's gonna, like I said, go from like here to here. It also requires a 300-foot long 3-span bridge. And then there's, a bunch more cut here. This is limited by this 6% slope, right? I can't go down any steeper to get a shorter bridge, or up any steeper to reduce my cut. And then I've got a culvert over here, and then a bunch of fill. And so I cut a few other sections, right? One at 300, one at 600. So one here, one here, one at 1,700, so here. And I did some cut and fill calcs, which you can kind of see. I have my start, my end, whether it's cut or fill, my section area, right? So that's like this. My total volume, which is just the section area times the length. And then I converted from cubic feet to cubic yards. And I come up with 12-yard dump trucks, 13,775 trucks, right? That sounds like a great project, right? Like that's going to take some serious, months and months and months of trucking. Mostly it's cut, right? So you got to get rid of that material somewhere. So that's project A, right? And again, there's a few notes here about how like it forces a long bridge and a big road cut, right? Because I've made these curves so big that I'm basically forced into this alignment, right? I can't really deviate that very much. And then project B, if I drop this to 20 miles an hour, then I get these little tiny 160-foot curves. And that allows me to come out of this tunnel, bank hard left, cross the river where it's much skinnier, bank right, go across this flat zone, bank left, and then go across the culvert, the stream where it's skinnier, right? And so the profile for that looks like this, right? You can kind of see that I'm following the land much more closely. I've got a balance, if you will. I've got some cut and some fill, not just huge amounts of cut. I've got a much shorter bridge. I've got some fill here because it's steeper. My bridge ends up being higher and taller. And so when I do that, and I cut a few things here, you'll notice this is a bridge. This is a cut that's a section that's really close to the bridge. 1550 is right here. And so you can kind of see I have these like called wing walls. We'll talk about those next week, 2 weeks. And so my cut looks a little different, and so in this case, I end up with a total net, right? This is the net total, right? Because you'll see that my fills are negative and my cuts are positive. But I have a net total here of only 54 trucks, which is basically nothing, right? And then I summarize those both here, and you'll notice, you know, again, I've got here I've got 200,000 cubic yards of moved dirt, right? So that's the absolute value of those numbers, net, and 170,000 cubic yards of net versus 700 cubic yards of net and 60,000 cubic yards of moved dirt, right? So that's like put it in a dump truck, move it over somewhere else and fill it, right? Take cut from here, fill from here. And sometimes you can just do that with a bulldozer. So anyway, this is kind of gives you an idea, hopefully, of how important it is and what. Now the question becomes, which one of these would we do? What's the problem with this one? It's slow, right? Also, it's not that safe, right? A lot of the DOTs across the country, their primary mission is actually safety. And so a lot of the places where you see road construction, especially of the nature where this is the old road and this is the new road, right, is because of safety. There's a lot of crashes, people going off the road, you need guardrails, all that stuff. People go too fast, right? The design speed was 20, but everyone's going 35 or 40. And so we're willing to spend a ton of money to build a long bridge and do a huge road cut in the name of safety, right? And so if you have the money, right? If you don't have the money, then you're stuck with this, right? So it's not always just about the money. Sometimes it's about the safety, right? But this is what you get when you don't have any money, right? So, okay. That's it. I will see you guys next week.